everyone. I'm Carl from the Estonian Student Satellite Foundation, and today I'm going to talk about our first PocketQube platform, SUTS. A little bit about what I'm going to talk about today. So first I'm going to give an overview of the Estonian Student Satellite, then describe the mission of SUTS a bit, then go into a bit more in depth about the architecture of the satellite, and in the end, we're going to look what's up ahead for this mission. So, the Estonian Student Satellite is quite a unique organization. As Estonia is such a small country, then we decided to group our student satellite building efforts from multiple universities under one organization, and thus the Student Satellite was born. So the main goal of the organization is to develop different satellites and in the process give valuable education and practical experiences to students. So a little bit about the earlier Estonian satellites. Estonia's first satellite, 𝗖𝗀 was launched in 2013, and it was quite a successful mission, even though the main payload didn't work. But the secondary payload, the cameras, got us very good images of Estonia, and as a first mission, we consider this a big success. Then in 2019 and 2020 were two identical satellites, 𝗖𝗀 and 𝗁𝗁, from the Tallinn University of Technology. And then in 2023, from the University of Tartu, it was the 𝗖𝗀 satellite, which sadly didn't reach orbit due to a deployer malfunction. So a quick overview of the SUTS mission. SUTS stands for Strategic Upgrades Testing Satellite. It will be a 3P PocketQube, and it will house multiple payloads from industry and academic partners. Currently, SUTS is expected to launch in 2028, but a bit more about the schedule at the end. The main goals of the mission are to provide a platform for our payload partners, Golbriak Space, Skudo, and TalTech. Also, as this is the first proper mission of the Estonian Student Satellite, then we wish to establish collaboration between different Estonian universities and even high schools. And of course, as this is a student project, then also to give practical engineering experience to students. So a little bit more about the payloads. SUTS has two payloads on board: optical communication module by Golbriak Space and Skudo, two Estonian private companies, and also a moon regolith solar cell test area by our own project manager, who is doing this as her PhD. A little bit more about the satellite platform itself. So as most satellites, SUTS consists of many different subsystems: command and data handling, ADCS, attitude determination and control, electrical power system, COM, and of course the mechanics. For the command and data handling system, this is the primary computation system for the satellite. It controls both EPS and COM, and contrary to a lot of others, we have gone with the Atmel S70 series MCUs. What I've seen from before, there have been a lot of SDMs and other MCUs around, but we chose this because in parallel in Estonia we're still continuing developing the 𝗖𝗀 line of satellites, and as the goal there is to go to deep space one day, then these MCUs can be, or there exists a version which is rad hardened. And there was also some thoughts about AI before. It seems AI won't be taking our jobs anytime soon, as this is supposed to be a 3P PocketQube. But probably the most critical system for SUTS is ADCS, as the optical communication payload requires very precise pointing, and this is very difficult to achieve in such a small form factor. So currently the requirement is that we would have 1 degree of relative pointing accuracy and 5 degrees of absolute. And for that, for the attitude control, for simulating the attitude control, we have created our own simulation environment. For determination, the satellite will have 5 sun sensors, gyroscopes, and magnetometers. And for determination, we will have 3 magnetors, which we aim to build in-house, and then 3 small CubeSat reaction wheels from Wittgenstein. And the current status of the ADCS is that the first main board with the MCU and sensors is almost ready, and we will do testing with different methods. For example, we also are developing custom air bearing and a rotating bench for different attitude determination, attitude control simulations. And we also wish to test all this equipment in thermal vacuum chambers to see how it holds up in conditions similar to actual space. About EPS, we have 2 lithium-ion batteries, and we have, as seen before, 3 sets of deployables, which will have solar cells on the other side. And then by the power distribution and management system, this voltage will be regulated into 3.3 and 5 volt lines. And also, for many systems, we have ditched the idea of redundancy because there just isn't enough space. But for EPS, we managed to keep some redundancy, that we have hot redundant buck and boost converters for the power lines. And about COM, this is what I am currently working on as my thesis. Unlike many other satellite systems for SUTS, COM will be a passive system, meaning it won't have a discrete MCU. We've decided to go this way to, first of all, reduce complexity and also to save space. It will have the Silicon Labs 446 transceiver and communicate on the 70 centimeter wavelength amateur radio band, most likely 437 megahertz, but we haven't gotten into the frequency coordination yet. This is something that we need to do as soon as possible. And it will have a quarter wavelength monopole antenna. Here on the right, you can see antenna testing in the anechoic chamber at the Tartu Observatory. A little bit more about the antenna, as it needs to be stowed during launch. Then we are using this antenna deployment mechanism, which features the coaxial connector as the hinge, and then a spring which will push the antenna open once it's in, once it has reached space. And another difficult part in mechanics has been the deployable wings, as these need to remain at quite a straight angle, and also the hinges and springs need to work as expected. For solar cells, we plan to go with Azure Space triple junction space solar cells, and as we have 12 of them, 6 on both sides. So a little bit about what's next. As you can see from the timeline, currently we're in the middle of the technical development. And this is expected to last until middle of next year or end of next year. We have a very ambitious goal that we want to deliver an engineering model by the end of 2025. Let's see how this goes. And starting to move away from the developing prototypes and starting to develop, integrate and test different systems. But thank you. This is it.